Okay, go.
Yeah. So, welcome everyone. So, today we have Dr. Maywin Lin. She is a NASA JAG-EDIT postdoc hosted by Dr. Andrew Pop at Space Science Lab, University of California, Berkeley. She received her PhD and MS degree from Department of Electrical and Computer Engineering at University of Illinois at Urbana-Champaign, advised by Dr. Laruka Elliott, something like that. Her primary research focus is understanding the heavy ion circulation in geospace environment through a combination of numerical modeling and data analysis. She was awarded the NASA JAG-EDIT postdoc fellowship in 2013. 2023. 10 years ago. Like, okay. And the NASA Venice Fellow. Okay, sorry about that. In 2021. Other than research, Dr. Lin is heavily involved in the scientific community as she served the student rep in NSF Geospace Environment Modeling Program and HAO NSP committees. She is also an organizer of Center for Investigative Planetary Science seminar series in UC Berkeley. So let's welcome Mary.
To clap my hand. Thank you so much for being here, and I know this is a quite interesting time to visit any place in the United States, and so I appreciate you spend that time in this next hour here, and I hope I'm not disappointed of your time, but I'm happy to talk about my research, and honestly, I don't expect to see so many people's face. I thought I'm going to be in the midterm for like only 7 chairs, so I was very happy to be here. Today I'm going to talk about my postdoc research, and that was to connect the moon and the magnetosphere together. I think this talk gave a new directions for our community. And when I first proposed this idea, everybody thought I was crazy, because the moon was always in another community, and how do you connect two things that are not related, are not working for a very long time? But I think the past less than 2 years, I see there's some probability, and now because of the uncertainty of the whole environment, I put the budget summary last year to the Google AI and asked them, can you summarize some good news and bad news for me? And then the ChatGPT or Google AI obviously told me, like, you need to do interdisciplinary research. And I think that's encouragement that I would like to give this talk, that we're trying to do interdisciplinary research in the next few years. I want to thank Zhiting and Sherry to organize the whole seminar and bring me here. And I know that everything is uncertain, so bringing me here must take them a lot of effort and time, so I really appreciate it. So let me get into it. I always start with the fundamental ideas, and my goal today is to give a new insight. But generally, in our geospace environment, we consider the source of plasma dominant by 2 resources. And that 2 resources have to be largely investigated in the HAO. The first one is solar wind. You have hydrogen ions, helium, alpha particles, which is helium double plus, and you have some heavy ions, but with higher charge state. So O6 plus, O7 plus, and Fe6 plus, Fe7 plus. But on the other hand, you have atmosphere and ionosphere that provide mainly the single charge state ions. And this has been known for a very long time, like atmosphere and ionosphere serve as a main source to provide heavy ions to the geospace environment, which is magnetosphere. And most of the people talk about O+. If you know me a little bit earlier enough, I was putting a lot of effort on other heavier species like nitrogen ions, N2 and O2 plus molecular ions. And how does that atmosphere and ionosphere serve, become a source of the magnetosphere plasma? And that just because the plasma transport, how the plasma transport in the Earth, ionosphere, and magnetosphere system. And you can think about this as mainly as magnetic field. Like magnetic field, you have magnetic flux tube that transport the ions from the ionosphere to the magnetosphere. And because the topology of magnetic field, you ended up with different pathways. So in the closed field lines, you have trapped cold ions that your ions will go from the ionosphere to the magnetosphere and back to the ionosphere, just how the magnetic flux field has been formed. But in a high altitude, I often refer to as a polaring outflow, just because that was like an outflow from the polar regions. And if some of you are working on the solar wind area, then you will know that the polar wing, when they named polar wing, that was similar to the solar wing. The solar wing is the ion outflow from the sun. So polar wing is like ion outflow from the polar region. So they just call it as a polar wing. And when they're first coming out the theory, actually the polar wing is exactly as the same as the solar wing. They just changed the terminology and changed the physics based on what we understand about the environment. So for example, in the polar wing ionosphere, we have more collisions, but we don't have that much in the solar regions. So give us some analogy about how we consider this. But at the end of the day, if you have trapped cold ions, you have polaring outflow, how the ion looks like, how the ion outflow looks like is you have this cold ion that's like blue torus regions surrounding the mid and low latitude, and then you have this warm and a little bit energetic ions in the high altitude along the open magnetic field lines. And in the past tens of years, we used an important indicator called oxygen ions to understand how the ionosphere contribute to the magnetosphere plasma. And what they do is they just detect the oxygen ions. We detect oxygen ions in these regions, and then we know how much of oxygen ion from the ionosphere. Then based on the topology of magnetic field, we can indicate different pathways. So then that's how we understand that some of the ions will go directly to the mid and low latitude, but some of the ions, well, they become energized and to the plasma sheet, and then they transport back to the inner magnetosphere. And I know like we have so many different people in this room, so if you are not familiar with the terminology, please just let me know and I can define it immediately. Then you can see there's a different pathways and different energization, and we use this oxygen as an indicator to understand the circulation pathways. In the past few years, there's a debate about how important between the ionosphere and solar wind. What is there? How much time does it take for them to reach the magnetosphere? And I'm gonna give you two examples. The first example is from one of my long-term collaborator, Alex Glosser, from the NASA Goddard Space Flight Center. And what he did is he runs a space weather modeling framework, and he tries to see, and he somehow separate out the hydrogen ions from the solar wind, hydrogen ions from the ionosphere, because if you see the hydrogen ions in the magnetosphere, you don't know where they are. They can come from the solar wind, they can come from the ionosphere. So the project is to understand what is the possibility of this H plus coming from the solar wind, and what is this H plus coming from the ionosphere. And he ran several times and during the storm. In the most of the time during the quiet time to the main phase of the storm, which is the most disturbed time, which when I say main phase of the storm is the most disturbed time in the magnetosphere, you can see, so this is ionosphere oxygen ions, ionosphere hydrogen ions, and solar wind hydrogen ions, and by the percentage. Well, you don't really need to know the percentage, you just see the colors. But during the most of the times, ionosphere is the main source of the magnetosphere. During the main phase, during the quiet time. But during the recovery time, which is the time after the main phase of storm, the solar ions start to take the place, which means in most of the conditions, you have the ionosphere H plus dominate the magnetosphere plasma. But at the end of the storm, the solar wind becomes a major supply. Another, because I know I'm coming here, and we have some people in this room are from the CGS Drive Center, and I really like this work is they are tracing the particle and the time and their pathways from different sources and how do they contribute to the magnetosphere, and using the CGS model. Then what they found it out is it's often take the solar wind particles to reach magnetosphere about more than 2 hours or more, which means in the beginning of the storm, ionosphere is the dominant sources, and the solar wind will become more important at the late phase of the storm. And that telling us that, so I just summarize it, ionosphere dominate most of the time, but during the recovery phase, solar wind will take over it, and it takes a few hours for the solar wind ions to reach the magnetosphere. But at the end of the day, that telling us, two studies telling us, we kind of know their importance and how we deal with that, but what else? So in this talk, I would like to switch the topic a little bit, like let's see, because both of them tracing the hydrogen ions, which is light ions. Let's see other heavy ions, and what can we tell from that? The right-hand side has been one of my favorite plot in this field. This is using a GeoTel spacecraft mission. It was a spacecraft mission from 1995 all the way to 2022, 27 years. It covers the magnetosphere from 9 RE to 30 RE, most likely. And there was the whole instrument was developed back in 1980s. And what they found it out, this is really complicated part to tell you a lot of information. The y-axis was the mass in the AMU, and x-axis, I forgot the legend, was m over q AMU divided by the charge state. So if you look directly, you can easily tell that, okay, the higher charge state, so this whole plot telling you what is the mass contribution, what is the charge state distributions. You can easily tell the higher charge state might come from the solar wind. And then you see a huge block of the oxygen and nitrogen, which is close to mass, close to 16, then you can distinguish, okay, they might be come from the atmosphere. But the interesting part of this figure is we see a lot of ions that their mass is over 16. So what is their importance is what are they? And where are they from? They are can be from solar wind, they can from the ionosphere, but if you want something from the ionosphere more than 16 AMU, which means really need a huge force to push them out. And what kind of sources is that related to the storm activity? So I think the fundamental question from this plot is, are abundances of these MR ions correlated to the storm activity? Well, the geomagnetic storm is the main source to push them out, or there's something else? So when I say MR ions, I'm not a person to talk about this name. It's from Kristen. But anions can be metallic ions, molecular ions that can be around 30 AMU. So NO plus, N2 plus. If you are talking about metallic ions, they can be sodium. They can be silicon, aluminum. So there are just so many candidates that we just ended up calling MR ions, just close to mass close to 30 AMU.
Can I ask a question?
Sure.
Just a clarification. What does it mean when the AMU is less than 1? It's quite a bit of color.
You say this?
Yeah, you're below. Is it one?
Yeah.
What is that?
Below the one.
Below 1. Yeah.
Oh, I know this. So as I said, like this instrument, and I talked to people who developed a similar instrument before, and they sent me a 100 pages manual. Now how they deal with that, I think that might be most likely the noise.
It's an instrumental effect of some kind, leakage or something.
Yeah, definitely. Then they can't even do like we observe FE 13 plus. We observe FE 20 plus. And if you do it all the time, it's like that was everything close to here, but they just did not distinguish. So I think H plus is something they develop, they maybe detect HE 3 plus, 4 plus, and something. And when they do the plot, they just like fall into less than one. But that's a great question.
Yeah, I guess the peak is above 1.
Yeah.
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 Okay. Like, what?
Yeah.
What is that stuff?
No, back in the days, they don't really open public data. But they do in secret. Just never release online. But yeah, that's something, if there's a time we can take a look at it. Thanks. Can I go to the next slide? So there are some studies about this MI ions. I don't know how to call it. I often call them molecular ions when I was a PhD student, but I need to call them as metallic ions. So let's just call them like mass close to 30 AMU ions, large mass ions. Let's say that. How do they depend? How do they depend on the solar activity? And the first example I give is from a Japanese mission called Arase mission. It was the Inner Magnetosphere mission, and they have a quite better, fast resolution instrument on the spacecraft. But this is really a preliminary spectrum that we often are showing this data to people because they don't really tell a lot of physics, but at least they tell us something. So the x-axis was time of flight beams and the y-axis was the counts. So based on the counts, you can get the relative contributions, but they cannot tell you what is their density, what is their fluxes. They just tell you what is their relative ratios. And you can see oxygen ions, hydrogen ions, double He, He double plus, He plus, and you can see some of the O double plus as well. But in addition to oxygen ions, they see a peak on the molecular ions. And during a storm time, and this storm, I think the DST was like, maybe the KP was only 4 or 5. And the minimum DST, which is what we call the minimum disturbed magnetic field, was only 17 nanotesla. So compared to, let's say, the May storm back last year was like 400 nanotesla. This storm was rather moderate. But they do see a peak in the molecular ions, and they cannot explain. Like, how do we have such a higher mass ions in the magnetosphere during even not disturbed time? Do we miss anything? And then this is another example from the geotel, also from Princeton 2020 paper. Again, they only show you the counts versus different conditions. So the left-hand side was F10.7 versus counts. Right-hand side was KP over the counts. You can see the counts is rather small just because the instrument itself doesn't have a sense of great capability to distinguish the ion. So they just give you some data, but there's not really a lot of confidence level. Which means the counts per 3 hours. So in 3 hours, you only see 20 nitrogen in the geotel data, and then you see 80 times of the oxygen ions in the geotel data. So that doesn't really tell you the fluxes, doesn't really tell you the density, but at least telling you the relative abundances. And you can categorize in different time, like different F10.7 telling you the solar activity, and KP index is telling you the storm activity. And different colors represent different ion species. So oxygen was blue, nitrogen was orange, and the large mass ions was the red and purple. One thing I found it out is, okay, those large mass ions doesn't seem to depend too much on the solar activity, but they are very sensitive to the storm activity. So one of the possibilities of we might have some energization mechanisms to pull those large mass ions out from the atmosphere during the storm time. And they are more sensitive to nitrogen and oxygen ions. So I think we want to take a step back to where are the sources. We see them showing during the storm time, but what are their sources? What are their primary contributions? I published a paper about the molecular ions, and that time I talk about how the molecular ions has been produced and interacted, and how do they probably contribute to those presence of higher mass ions in the magnetosphere. But there's a thing I'm missing in that paper is I didn't include the metallic ions, which the mass was close to mass over 28 and 30 MU. And then I have a conversation with the people from planetary, which is doing the moon, and they say, have you think about this large mass ions coming from other species? And maybe they come from different sources. And there's a commonality between the ionosphere and moon that they might contribute the similar ion masses that you didn't think about it before. So one of the candidates was the metallic ions, and they are deposited to the ionosphere all the time. And we see this deposit species because we have comet and we can see these meteor showers, and they were coming to the Earth atmosphere, and you can see them. But one thing is so you can see that when they coming through the ionosphere, you can see they will have this sodium layer because they deposited sodium to the atmosphere, and it's just really easy to see them because the sodium, you can detect the sodium lines, and so you can tweak your camera and say, I only wanted to see the sodium coming from. So that's how this picture is coming from. But essentially, through the meteorite shower, ablation of the meteorites, you can deposit different kind of metallic ions, like sodium, magnesium, aluminum, silicon, potassium, calcium, and everything. But we don't really talk about how they are doing above the atmosphere and ionosphere. I know there's a huge community in this lab, and I'm happy to talk more talk about how the metallic ions have been transported or like neutral metals. But that really not a lot of effort spending on like how those ions transported upward to the high altitude. So when we see that those large mass ions, we often not consider the metallic ions just because there's unknown transport mechanisms. We don't know how do they deposit, how much do they do, and where are they going afterward? So we just simply not work on that topic because we just don't have that mechanisms in the community to push it forward. But the same thing, if you the deposit species not only happens on Earth, but happens on different planets. So for example, the moon, because you also have a planet, and then you also have a meteorite or like solar wind impacting the surfaces. So they could have metallic ions and generated from that. I don't have expertise on atmosphere and ionosphere. I'm not doing metallic ion deposit in atmosphere, but I worked with people that doing the moon's research. So we decided to switch up topic a little bit and see what is the probability for the lunar to generate metallic ions, and what is their transport mechanism, because the moon is so far away from the Earth. Moon was 60 Earth radius away from the Earth and was like orbiting around the equatorial plane. So if you have the magnetosphere, Moon is spending about 5 to 6 days per month in the magnetosphere, and other of the day they are in the solar wind. So my work from this talk is we would like to see how the metallic ions deposit to the moon and what is their transport probability to the magnetosphere. And one of my motivation is actually, again, the geotel data, because we don't really have any other missions that can give us a better resolution on the higher mass ions. What they do is they categorize the data based on the lunar locations. So as I said, 5-6 days lunar was spending on the magnetosphere, which is the tail part, the zero part, and then gradually turn to 1, 2, 3, 4, 5. So they just divide the lunar orbit to 6 parts. And this plot is during the storm time. So we can also categorize to storm time and quiet time. One thing they found it out in different colors was different species, and again the y-axis was the counts per 3 hours and the x-axis the local lunar time. Remind is there didn't give you the fluxes, didn't give you the density, just give you the relative abundances. But you could see that the large mass ions, including mass around 30, 40, and irons, they are depend on where the moon is. When the moon is in the 3, which is during the solar wind upstream, they see more large mass ions in general in the magnetosphere. And they just basically doing the same thing for different conditions and different locations, and see if there's a dependence on the metallic ions or like large mass ions within the lunar locations. In this paper, they say no, nothing is related. Everything looks flat. So we shouldn't talk about moon in the paper. But I don't really agree with that. I can see there's a dependence on the large mass ions abundances with the lunar locations. And it's kind of quite strict when you say they are quite flat. So there's definitely a debate. So what should we do? And I think we have to back to the physics, the fundamental physics. How did the metallic ions has been produced on the moon? And what is their transport mechanisms from the moon all the way to the magnetosphere? So we know there's a lot of metallic neutrals around the moon. And why do people know? Because they see the sodium exosphere around the moon. So the left-hand side is the moon with the sodium exosphere. Just what we see from the previous slide, you see the pictures with a sodium layer. That's like similar technique. People use the similar techniques to also detect the mercury as well, and they see sodium around mercury. So just similar techniques around the whole universe. Then how does this sodium neutral has been deposited to the moon, and then make acute animation that everything hitting on the lunar surface will kick out, I can be the animation, but you can see they are hitting on the lunar surface and they will kick out something from the surface. So there are two mechanisms. The one is called solar wind sputtering. You have the solar wind ions, including hydrogen ions or helium double plus ions. And when they hit the lunar surface, they can kick out the neutral metals. And the same thing happens for what we call micrometeorite impact. Just like what we did on the Earth, we have meteor showers. They also have micro scale of the meteorites hitting the lunar surface, and they can kick out the neutral metals as well. And one of the fundamental difference between the moon and Earth is Earth has the atmosphere to protect us. We have a magnetic field, but moon has none of them. Moon doesn't have a global magnetic field. Moon didn't have a thick enough atmosphere. So everything hitting to the surface will be kicked out eventually. And the lunar surface has the large percentage of the metals from the surface, about 30. So this is back in Apollo era, they collect the rock and they detect. They're trying to look at their composition, and they found it out about 30% of the lunar soil is composed of the metals, which means if you have any impacting particles to the surface, around 30% of the probabilities, you can kick out the neutral metals. And when you have the neutral metals being kicked out, they can undergo ionization processes and they become the lunar peak ions. So from neutrals to become the ions. And this technique has been implemented in the moon community for a very long time because detecting neutral is hard, but detecting ions is easy. So they detecting the ions, and then that's the way they could identify how the lunar atmosphere looks like. This is an example again from the Japanese spacecraft called Kaguya, but this is a very short-term spacecraft mission, only 1 year. And you can see they don't have a fancy instrument like Earth did. They just use a very preliminary instrument to identify the species. So I always call them Carol plot because you only see a lot of hydrogen ions and helium double plus, and you see nothing more. But they do some calibration, and they did trying to distinguish the species from, you can see oxygen ions, you can see sodium, you can see aluminum, and that's the way they could identify where the neutrals is and where the ions looks like. So one of the conclusions they have from the moon community is, unlike Earth, the atmosphere is, the high altitude atmosphere is composed of the light ions. The moon actually provides a lot of large mass ions, and their mass is close to 28 and over 40. And they have a community that they're trying to distinguish what is their contributions, like how much aluminum, how much silicon, how much is argon-40, how much is potassium. But we can actually use this information and estimate how the lunar peak ions looks like. And one of the new contributions to this is, what is the variation of the metallic ions during the lunar orbit? Because in the magnetosphere, your environment is quite different from the solar wind. So how does the metallic ion distribution looks like in addition to the solar wind regions? I've just realized I only have 22 minutes, so I have to speed up a little bit. But the idea is, if we know how the lunar exosphere looks like, if we know how the ionization process looks like, then we can know how the lunar peak ion fluxes looks like. That's the fundamental idea. And how do we know each of them? Well, and then that's where the magic comes from. In the moon community, they don't care about the magnetosphere. In our community, we don't care about the moon. So how do we connect things together? Luckily, there's a spacecraft mission, sub-spacecraft mission called Artemis Themis. We don't have Artemis anymore, so we can call Artemis right now. Artemis Themis is two spacecraft from the Themis, and they send it to the moon. They're orbiting around the moon, and they're trying to distinguish, trying to identify the moon's environment. The Artemis Themis doesn't have the time of flight elements, which means that they cannot distinguish the species, but they can give you the total impacting ion fluxes. So what I do is I use the Artemis ESA data. I know how much impacting particles to the lunar surface. Then based on what I understand about the lunar environment, I can derive the lunar exosphere composition and the ionization rate. And with those two elements, I can eventually derive the lunar peak of ion fluxes. It looks like a magic, but it's not really like that. It's the first one is how does the lunar exosphere has been formed is the impacting particle fluxes, and then how does the impacting process looks like. Then you can derive the sputtering rate. From sputtering rate, which how much ions has been kicked off on the surface, then you can derive the production rate of the neutrons. So the lower panel shows you the impacting particle fluxes from the spacecraft. You can see there's a narrow beam from detected, which means this actually is from the solar wind. In the solar wind, you will always observe a 1 keV solar wind beams. Then when you are entering the magnetosphere, you don't have solar wind anymore. It turns out to be the magnetosphere environment. So this shows you that during a typical month of the orbit, which the x-axis was the month and y-axis was the energy spectrum, the moon will transition from the solar wind regions to the magnetosphere region and back to the solar wind. Thanks for reminding me of time. Then you can even see how much time they spend in the magnetosphere is about a week, so 5-6 days to a week. Even during this spectrum, you can distinguish the magnetosphere environment. That solar wind is a narrow beam going to the magnetic sheet. It becomes a little bit broader in energy range. In the magnetotail, it's rather quiet, so you don't really see a lot of fluxes, and but you see a wider energy range, and that will back to the solar wind regions again. From those, you can even identify the neutral magnesium fluxes. So in the solar wind regions, you have a lot of neutral magnesium has been produced because you have a lot of impacting particles. But during the magnetosphere, because you don't have a lot of impacting particles to the surface, so they just becomes nearly zero. And that's back to the solar wind again, which means the magnetosphere is a really good shielding to protect the lunar surface to be impacted. And that time, you don't really have a lot of metallic neutrons, metallic ions generated on the lunar surface. The other thing I look at it is the ionization processes. Even you have the neutral metals, you still need to ionize them. So the spacecraft provides you the impacting particles. So based on the impacting particles, the electron fluxes, the high ion fluxes. And then based on that, you can calculate the electron impact and charge exchange processes. So what is the ionization process look like. Here I show you the electron impact rate and proton charge exchange rate with the photoionization, along with the solar activity. The x-axis was the year and y-axis was the sunspot number. So just you can see how how each ionization processes vary by different times and different solar conditions. Photon ionization was the dominant ionization processes, and electron impact and proton exchange, they are not that important. But they also don't vary too much with the solar activity. So you can kind of tell that actually the neutral metallic ion production is a key role because ionization processes basically just vary with the solar activity. The third part is how much do they produce? And one thing I didn't talk about here is you only produce ions when they are not ionized quickly enough, just like Earth. So the process is when you kick out the neutral metals from the lunar surface, they will going through the ballistic travel. And during the ballistic travel, they have probability to become ions with the electrons or protons. But if those two processes are too slow, or like for ionization, if those two processes are too slow, then they will become the neutrals and back to the lunar surface. So you only generate the ions when their processes are quickly enough compared to the ballistic travel time. Then you can get the metallic ions. And we think this is the physics that how do we generate the metallic ions near the moon. It's not only compared to the soil looks like, how the solar activity looks like, that also compares your travel time versus your ionization time. So that makes the whole work more dynamic. So what we found it out is in the beginning, I say there are two processes to produce the neutrals, but they are all like kick-out processes. The first one is solar wind sputtering, and the second one was the meteorite impact. But it turns out the solar wind sputtering is the major process because they often generate energetic ions and energetic neutrals from the lunar surface. There are more energetic particles impacting the lunar surface. But on the other hand, the meteorite impact is a rather minor impact. They will hit your lunar surface, but they didn't kick out an energetic enough particle that they can survive to be ions. So, which means that give you like if you understand the neutral metal fluxes, you have to times with those production rate and becomes the ion fluxes. So at the end of the day, this project is to tell you how much fluxes could be possibly generated near the lunar surface. And I can give you a typical number that the metallic ions fluxes near the moon is about 10 to 5, 10 to 6 per centimeter cube per second. And compared to the Earth, I can give you another number. For the Earth, the ion fluxes is often varied from 10 to 5 to 10 to 8. So oxygen ions could be 10 to 8 per centimeter cube per second. But other species could be like 10 to 5, 10 to 6. So interesting enough is actually, if you compare with the fluxes, sorry for everything. I can come back here later. If you compare everything together, in the large mass ions, you have comparable contributions from the moon and the Earth ionosphere, just in the large mass ions, because their fluxes are very close to each other. So this plot showing you the escape rate for different species. So you have oxygen ions, nitrogen, hydrogen, helium, and then you have a bunch of metallic ions and a bunch of molecular and metallic ions. And when we calculated with the area of the Earth ionosphere and also the area of the lunar surface, we found it out they could contribute similar amount of the large mass ions to the whole geobase environment. And that back to my previous slide that we often thinking about the large mass ion sources, but this research telling you they could be both coming from the moon or the ionosphere because they just essentially provide similar amounts of the large mass ion fluxes to the whole geobase environment. And the reason I would like to be super quick in the previous project is I want to share our latest result is the next question is, will the lunar peak ions reach magnetosphere? We know the ionosphere ions could be easily reach the magnetosphere if they are energized enough, but the moon only spends 5-6 days in the magnetosphere. Could we have those large mass ions reach the magnetosphere just within their orbit? And I call this what I call like space weather on moon. But my method, sorry for the slide, but my method is I just use the MHD plus the particle tracing code, and I would like to see could we have the particles from the moon reach the magnetosphere just when the moon is passing through a magnetosphere? And could we have that? And how does their dependence with the solar, the geospace conditions? So my first slide I want to show you is I just released multiple particles from the moon, and the Earth is here. So moon was in the night side, and the pink trajectory marks when the moon's particle reaching the magnetosphere, and the gray line means they just not reach the magnetosphere anymore. We found it out there's a possibility that we could have the particles from the moon reaching the inner magnetosphere, and they can be even trapped just within 2 hours or 3 hours. And this was slightly different from how the solar particles reaching the magnetosphere, because moon is actually in the magnetosphere. So you don't need 2.5 hours to reach the magnetosphere. They are there. They just need some transport time to be cached in the magnetosphere. But this plot telling us that there's a possibility you can have the large mass ions being kept, they are coming from the moon, being catch up in the magnetosphere. And that telling you that both of the answers are possible. You can coming from the atmosphere, you can also coming from the moon. The condition that running for this simulation, they are during the storm time, but it's not a huge storm. It's just KP, I think KP is like 5. So it's like moderate storm, just like what the example I just showed before. But another thing, which is served as my last slide, so we can go to the discussion, is what does their fluxes look like? So I just basically reach a lot of particles from when the moon is here in different locations and trying to see how do they transport to the magnetosphere. So Earth is here, moon is here, and the orbit is like this. So the sun is always in here. And one thing I found it out is this mechanism is very narrow to where the moon is. They can only transport to the magnetosphere when the moon is super close to the equatorial plane. So if your moon, maybe just like a day, that the moon has possibility to transport ions back to the inner magnetosphere. Another 29 days per month, you don't have the possibility for moons to reach in the moon's ions to reach the inner magnetosphere. So this is the possible mechanisms, but they are very narrowed down to when the condition is and where the moon is. So from here is about, you have to be 2-3 degrees above or below the equatorial plane, and that is the only conditions you could have the ions transport to the magnetosphere. Then the last thing is I running the idealized storm. I trying to categorize that we know where the moon needs to be super close to the equatorial plane, but how about the geomagnetic storm activity? So I run different BY and BZ conditions, and the conclusion is you only have the moon's ions reaching the magnetosphere during the north IMF conditions. And the reason is you only have the earthward flow presenting in the moon's locations during the northward IMF. So when BZ was like 10 nanotesla or 5 nanotesla, and your moon's super close to the equatorial plane, you can get the moon's ions to the magnetosphere. But other condition, you don't have that. So that going to my conclusion is we talk about the moon and ionosphere serve similar magnitude of the large mass fluxes to the magnetosphere. And I'm trying to quantify what is the probability for the moon's ions transported to the magnetosphere. And the conclusion is 2. The moon needs to be in the right time and right place. And the right time means you need to explain northward IMF. The right place is then you need to be super close to the equatorial plane. But what is the probability for those two things to be happening at the same time? I don't give a fair point. I will not say like one of them or the other is important. But I think that's telling us that the knowledge of what we understand about the geo-based environment will be useful to quantify how the environment changes on Mars and Moon. Then there's a possibility for us to implement those ideas that is essentially in the beginning of my project, I thought moon was super important. We don't have to take care about it first anymore. But if you quantify those ideas about where the moon is and where the condition is, you cannot quantify how the moon's environment look like without understanding how the geospace environment look like, how the solar activity looks like, how the moon's orbit looks like. You really need both knowledge to understand where those ions coming from. How do you generate those ions? What is their transport mechanisms? And I think I will not say like metallic ions you catch from in the magnetosphere must come from the moon. But I would say there's a portion of the metallic ions or large mass ions you see in the magnetosphere that probably come from the moon. But the probability is you need to be in the right time and right place. And what we learn from here in a geospace environment is a very useful knowledge resources for us to understand the planetary environment in other planetary bodies in the solar system. So that serves as the conclusion of my talk. Welcome any questions.
So did you explain why northward IMF? Why northward IMF? Why is that a criterion relative to southward IMF?
You need to have the earthward flow.
The earthward flow
Yeah, so
from the location of the moon.
exactly. So
Yeah.
what I'm showing here is the earthward flow during the lunar orbit, and the white place is where the earthward flow is. So you only get the earthward flow during the IMF. We don't really see that earthward flow during the southward IMF.
Because the reconnection line is earthward.
Reconnection line is too close to the magnetosphere, so you only get the tailward flow.
Is anything known about the effects of these metallic ions or heavy ions, not oxygen, nitrogen, et cetera? I mean, the super heavies, okay, on the geospace environment besides being present. Do they have any like dynamical effects, change the structure of geospace?
You see, like where,
Objective to just know whether they're there.
yeah, I think it depends on which species you talk about it. That if you're doing the molecular ions, because molecular ions right now is only 3% of the oxygen ions. You can only see them, but you cannot like quantify their environment. Like they don't play a huge role on the dynamics overall. Like they cannot really affect the recurrent decay. They cannot really affect it much of them. But one thing I would be super interested, because I'm going to talk about my idea, is for example, if you have the solar heavy ions, O6 plus, you can do charge exchange with the geocorona. Then that can affect how the geocorona formation looks like. And I think that's why people having like a SMILE mission and cruiser missions, they wanted to see how does the heavy ions interact with the geocorona and how does that too. Because the heavy ions is, larger, like their cross section is larger, they can easily do charge exchange with those ions. Then by identifying for example, for the solar ions, O6 plus, they can do charge exchange with a neutral edge, and they release this X-ray. So if you observe the X-ray, you can identify where the magnetosphere looks like, the boundary of the magnetosphere and magnetosheet. So even though they cannot directly contribute like recurrent decay or like recovery phase of the geomagnetic storm, but you can use the heavy ions to indicate where the boundary is.
Okay.
Yeah.
That's an interesting application.
And I think that is essentially happening to here. Like for here is we use the moon's ions to identify the boundary of the lunar ions because we often thought lunar is restricted to its area, but it turns out part of the lunar ions by tracing the heavy ions that could be reaching out to the magnetosphere.
Any other questions?
Any question from online people?
So one comment, and that's just that the physics of the generation of these is the same thing happens at Mercury, right? And so it's responsible for the atmosphere, contributing to the atmosphere of Mercury and ionosphere, which is rich in heavy ions. And so I would assume that you can borrow from some of that literature to check your calculation of production rates and so forth. I don't know if that's part of your research problem or not, but.
Yes or no, so for those planetary missions, they don't really have
They don't have
well-known data set to support their physics.
right. They don't have the McFadden's electrostatic analyzer on it, for example.
Exactly. I think we share this similar resources and citations, but none of us have validated resources. I will put this way. When I started this, I hope the Lunar Gateway can be a thing to verify my results, but unfortunately, Lunar Gateway become Mars Gateway at this point. So I don't have a validated resource at this point.
Well, but if only the moon could develop volcanoes like Eos. It would be very much more.
We got a whole other suite of problems at the moment. But
Okay, if there's no further question, let's thank our speakers again.
you might be able to